Hello, everyone. Welcome to our presentation with respect to the Deep Reinforcement Learning project for Northwestern University. We are dealing with Snake and Ladder, the game, and we are trying to solve this with Deep Reinforcement Learning. Just a quick background about the game. It's basically a game of chance where we have a die and the outcome is from 1 to 6, and based on the number provided, the user has to move from the starting state till the end state. And there are two factors over here. One would be the ladder and one would be the snake. And if you have the snake, that means it moves you further away from the goal, which is an unideal state. And if it's a ladder, it moves you closer to the goal. And the end goal is 1000 in this case. We're having a sample space up to 1000 where the action is a die roll from 1 to 6, and the rewards for each roll would be the following. So we have plus 10 for reaching the final goal. We have minus 10 for landing on a stake because it takes you back to the current position. And we have plus 5 for landing on the ladder, which moves you closer to the goal. And we have minus 1 for each non-goal step. Non-goal step meaning if the step is neither a snake nor a ladder if it's not the final square. Therefore, in order to make the agent learn quickly and move further towards the goal, we are having minus 1 as the reward point. Moving on.
Yeah, thank you. So Q-learning is one of the basic deep reinforcement learning algorithms. Here, what happens is that you'll be having a Q-learning table which will be initialized with 0 values, and the dimension of that table would be number of states. If for in our case it's 1000, and the number of possible actions that it will be from 1 to 6. So the Q table will also store the expected rewards for each state action pair. Coming to the algorithm itself, start it will begin each it will become by player with player starting at the starting position, and then it will repeat until it reaches the terminal state. And uh, for each and every state it will be considering the greedy policy whether to go explore or exploit based on it, and then take action, then observe the reward, and then go for the next state. So it reduces the come over time to balance the exploration and exploitation. That's how the Q learning works. And based on this, we got the average reward as 21.38 and the average steps at 17.62.
Right, coming to the SARSA algorithm, it is an on-policy temporal. It is an on-policy. My bad. The temporal difference learning algorithm. It updates the Q value based on the action actually taken, not the maximum possible reward. The update rule is right in front of you. This algorithm is more stable in environments where the policy changes over time. And the results that we got using this algorithm were that the average reward was around 21.85, and the average steps taken was around 17.15 to reach the goal state.
Thank you, Karan. Now moving on to DQN. DQN, Deep Q Learning. That is basically an extension of deep learning in deep reinforcement learning. Funny, right? So we're just trying to see if how well this is going to implement with respect to our game. So moving on, Deep Q Network, it basically helps us with experience replay, as in it stores the memory of each state and the action taken and the reward received. Therefore, it helps the agent learn by performing the memory buffer and batch learning. Moving on, with respect to the architecture of the DeepQN, it's basically consisting of a normal neural network, which has an input layer, the hidden layer, and the output layer. And the hidden layer has 2 layers, and the output layer has 6 outputs, one for each possible dice roll. Moving forward, the results we are getting with respect to the DQN is the average reward is minus 32 and the average steps is 55, which is pretty unlikely compared to the other algorithms. Thank you.
Right, coming to the discussion and overview slide, talking about the training time. So Q-learning and SARS are trained faster due to simpler computations. DQN took longer due to neural network updates. The expected versus actual results. Q-learning and SARSA performed very well as expected, while DQN underperformed, needing more hyperparameter tuning and the more experimentation with the architecture. Parameter tuning, critical parameters that involved were exploration rate and that eta and learning rate alpha. Challenges we faced were about more balancing exploration versus exploitation, and the DQN in DQ for the DQN algorithm, the network's complexity and stability. For the future work is to explore advanced RL methods and to refine the hyperparameters.
Thank you.
Thank you.